I would like now to discuss with you the generalization of the AllDifferent constraint. An easy generalization is, instead of requiring that every value should be taken at most 1 here in the variable value graph, we could instead specify a range of possible number of occurrences for each value. For instance, here, what I'm stating is that the value 3 should be matched exactly once, okay? And that's the case here. But this one should be matched between 0 and 2 times. It means that, and you see that it's the case here, the value 4 is taken by 2 different variables. Here I ask that this value 5 is taken between 1 and 3 times. And we could have a different range of possible number of occurrences for all the different values that you have in the variable value graph. Of course, that's a strict generalization of the AllDifferent constraint, because for the AllDifferent constraint, what we had is that we had between 0 and 1 for all the values, right? And that ensures that every value is taken at most once, and as a consequence, all the variables takes a different value. This generalization was proposed by Jean-Charles Régin, and the filtering algorithm was described in this paper published in the CP conference. How do we do the consistency check for that constraint if you want to be sure that if there is an inconsistency, we can detect it? And if not, it means that there is at least one feasible solution for the constraint. We can do that using the maximum flow algorithm. So we are not exactly working in the bipartite graph as before. We will add here a source node and a sink node. So we have a source node and a sink node there. Okay. In the middle, you have the bipartite graph. Okay, it's also going in that direction. All the edges, they go in that direction. But what you will do is that you will enforce some cardinality on the flow. So clearly, on that edge, you should have exactly between n, and n is the number of variables that you have here. You should have exactly n units of flow going into that edge. And in terms of the cardinality, if they must be matched, you will say that the cardinality of the flow here should be exactly 1. And for instance, for that edge, you should have between 0 and 2. So you specify the lower bound and the upper bound on the amount of flow that you would like to see in the maximum flow in this graph. So that's a strict generalization of the AllDifferent constraint, and I do not enter into the details of computing which edges should be removed, so how you do the filtering, but it's also exactly the same idea as the one we did before. You can reuse the Birch theorem and compute the surrounding connected component at once to be sure that you can safely remove and identify the edges that needs to be removed that do not belong to at least one maximum flow in this case, not a maximum matching, but a maximum flow in this case. So that was, again, a nice illustration of how we can embed existing very efficient graph algorithm inside the filtering algorithm of the global constraint in constraint programming. And that's an illustration here of the maximum flow algorithm, a well-known graph algorithm that you can reuse and to help you to filter the domains of the variables for global constraints.